Well, good morning. This is Thursday morning, I think the 27th of July, 2017. It's supposed to be differential equations, Math 238. It's already 8:14 at least. I've been waiting. The PowerPoint was having a hard time opening this morning. Screencast-O-Matic was a little slow itself, but finally everything's open. But nobody else is in the room but me. So this is the last day of class. I was hoping y'all would be here today to turn in your last work and to pick up your final. I hope you'll be coming in before the class moves on. Let me just say a few things about the end of the term, what's happening. First, let me say this. I was checked with students in other classes and found out indeed they are doing student course evaluations this summer. In the past, sometimes they do it in the summer and sometimes they don't. I hadn't seen or read anything about it, but a student said, or some of the students said, they had seen them, they had done them. So please, I want to ask you, please do the student course evaluations. Now, I know Marcus knows how to do them because he's been here. I don't know for sure if Megan does or not. So if you don't know how to access this, if you access your Lawson State email, I'm pretty sure you'll find then an email telling you about the student course evaluations, and that email will have a link. All you have to do is click on it, go to it, follow the instructions, log in. By the way, your login will be your, pretty sure it's your student ID number, which I'm guessing for Megan is probably a 1, 2 something another number with 5 more digits, 7-digit number, probably starting with 1, 2. Marcus, you probably have an older one than that, so it's probably 1, 1 or something there for your first 2 digits. And then once you log in with your Lawson State student ID, then your password is your birth date, and I'm pretty sure it's a 6-digit day, 2-digit month, 2-digit day, 2-digit year. So, but the prompts are there. They tell you what to do, how to do it, so please log in. Now, I was told by one student last night that that there were no additional things they asked for. Of course, we want your student course evaluation, but occasionally in fall and spring they usually put other things out there like registration procedure, bookstore, library, food service, groundskeeping, something like that. So far, I haven't heard of anyone having any of those additional ones. If they are, they're really short and you can take care of them pretty quickly. But please do the student course evaluation. Please. That's a great source of feedback. I get feedback from you every day, but I like to have when you can be a little more anonymous about it because I won't know what either one of you puts down on anything. I just see the composite. So please give a good, honest feedback there. Okay, now I'm planning to give out the test. That's one thing I took a little time on this morning, making sure I had the test prepared. I think I found 2 copies, so it's ready to go, but you're not here to get it. So if you don't come in today to pick up your test, please come in Monday and pick it up because technically it's due by Tuesday, but I will give you until Thursday, but please no later than Thursday noon. Now let me see, I believe only one of you has done your research paper. Both of you turned in your first test, and I can return those to you. I was going to do that today if I haven't turned them already. Second test I don't have yet, so I was hoping you were going to turn that in today. Haven't received it yet. Now, I apologize that I had to cancel class on Tuesday. I think I explained it in the email. We had our, and I told you in class actually before too, we had our planning hearing Tuesday. It was scheduled for 10 o'clock, so I knew I was going to have to leave class on Tuesday no later than 9:30, but I feared because I hadn't gotten all the data in from the other instructors, and one in particular didn't get me the data until Friday, okay? And I was home and had to work it in with the other data. There you go. Marcus is here. Good deal. I've got to ask you, did you come Tuesday?
I
You saw the email, good. I'm glad you saw it. I don't know about Megan, I don't know if she caught it or not. I'm just going over end of the term activities. I'll take you've already turned in your research paper, right? Okay. And I've got your first test. Did I return it to you? Okay. I can't return your research paper because periodically they ask for samples of student writing. So there's your second test. No, there's your first test. I'm sorry. I need the second test as soon as you finish it. You do have it still on it. Or did you turn it in already? I still have it. You still have it. Okay, good. So get that to me as soon as possible. And at the end of class today, I'll give you the last test, which will be last test, final test. Sorry. But I was apologizing for having to cancel class on Tuesday. I told you all last week that the hearings are coming up and I have to end class early at least. But I told you there was a chance I was going to have to cancel it too. I hoped I wouldn't, but one of the instructors who requested some of the specific outcomes never got me the data from those, and he's the one who had them. And so I contacted him on Thursday to say, look, I really need these. I'm putting them together today, Thursday, and hope to finish that. He said, I'll get them to you tomorrow, okay, which was Friday, my day off, and it was not early Friday he got them to me, it was late Friday, so I spent the rest of the weekend mixing that stuff in with the other data I already had prepared, and then writing up the results, but he said, I'll get you the documentation next week. Well, the documentation is almost as important as the data. So he hadn't gotten it to me Monday, so I knew I had to go in early and get it from him Tuesday. I couldn't wait until 9:30 because I couldn't guarantee he'd have it. Well, it couldn't be 9:30 because if I left here at 9:30, I'd be there right at 10. So I had to go straight there and take care of things there. So sorry that I had to cancel class. I really didn't want to. So what I want to do today is go just as far as we can. Have you got to leave early today? Okay. Well, before you go, pick up the final exam. Okay. The last exam is test 3. It actually says test 2 at the top, but it's test 3. Okay. Now, when is that due? Oh, let me say this for Megan's purpose. If you get me your research paper today, I'll still give you the 1 bonus point. If you get it to me Monday, you just get your score. If you get it to me Tuesday or later, you start losing points. Okay, so there's a bonus point today, no bonus points on Monday, negative bonus points next week after Monday. All right, please get me the second test today and pick up your first test. And I'll give you the last test today at the end of class and let you know how far to go on it because, well, if you're leaving early, you'll just have to listen to the YouTube video to find out how far we got. So, now, when is that due? Technically, it's due Tuesday at 8 o'clock or whatever. I don't hold to that. So, I say if you get it to me anytime Tuesday, anytime Wednesday, or anytime up till noon on Thursday. I'd really like to have them all in by noon on Thursday because even though next week is the first, we go into August and then we start working Fridays again, I won't be here on Friday because I have an infusion that was scheduled months ago, okay, for Friday morning. I think 7 or 7:30, so or maybe 8 o'clock, but I have to be there for labs by 7. So there's no way I can accept anything after Thursday. I'd like to have it before noon on Thursday. I'll be here till 5:15 on Thursday, but I can't be here any later. So please get, it into me by then. All right. And you see, I think grades are due in by noon on Friday, but since I'm not going to be here, I have to have them in before I leave Thursday evening, 5:15 on Thursday evening. So please try to get me the stuff as early if you finish it at Monday. Bring it Monday, okay? I'll take it Monday. I'll be in class all day, and that's true for the paper too. I have an 8 to 10:40 class. I have 20 minutes, and I usually try to just get back to the office for a bite to eat or something, but usually don't have much more than time for 1 or 2 bites. And then I have a class from 11 to 1:40, and I have another 20-minute break that I try to get to the office for just a few minutes. And then I have a physics class that starts at 2 and goes until 3:30. Now that one probably will end a little early because I think that class is mostly going to be passing out work and doing the lab. I think that's all we're going to be doing in that class because actually most of them weren't here yesterday, so I'll be giving them the final exam. But we finished that last chapter no, we didn't. I think I have 2 physics classes. I'm getting confused which one I finished and which one I did. So that first class I'll probably finish a little early. The second class, the odds are we'll finish a little early on that too. So I will be here, but the best idea, if I'm not in the office, slide it on my door. If you really need to see me, come up to the classroom because all 4 of my classes are here. As I was saying, I have the physics class from 2 to 5:30. It's class and lab. And then another physics class, 5:30 to 9, again, class and lab. So but both of those will probably end a little earlier just because it's the end of the term and we won't be having either the one class both classes, we will be doing the last lab, and I'll be giving them the last test too. So they'll probably finish earlier than normal because they won't have nearly as much lecture time in that. All right, any questions about how the end of the term is going to go? Okay. Any questions on differential equations? Okay. We were on page 128. This is chapter 4. That's higher order differential equations. 4.1 preliminary theory linear equations. So that's what we're doing now. And here's Megan, perfect attendance on the last day of class. That's good to see. I did want to find out, did you get the message before Tuesday?
Yes.
You did? Okay, good. All right. Let's see. We go over just the brief paper due. If you get it to me today, okay, then you get 1 bonus point. If you're going to turn it in today, I'll leave off the rest of it. Okay, your second test, neither one of you turn. Oh, let me give you your first test. I meant to give this earlier because after I got them all in. So here's your first test. And as soon as you can get me the second test, that will be great. Now, here's another thing I was explaining about because of that hearing. Basically, since last Tuesday, not day before yesterday, Tuesday a week ago, since then, literally, I have had 0 time to grade. And that's why my grading has piled up like this, okay, and more to come. Now, part of the reason for that, of course, my Monday, Wednesday classes, I go 8 in the morning till 9 at night. No time to grade that. I have 2 20-minute breaks and 2 10-minute breaks. And most of those are eaten up answering questions with students and stuff like that, or setting up labs and things like that. So 0 time on last Wednesday, Monday, or yesterday. 0 time to do grading, okay? Last Thursday, when I was advising students, I was spending just about all the off hours I had getting ready for that planning hearing and contacting people who hadn't gotten me the data yet. And so I got that stuff done as far as I could. Actually, one guy sent me the data on Friday, my weekend, time off, and I meshed that in with the others and wrote up the stuff, but he didn't get me the documentation until he said, I'll get it to you next week. Monday, I didn't receive it, so I had to go in early to get it on Tuesday. That's why I had to cancel class. Sorry about that. So all Thursday was spent doing that. Then, of course, Monday and Wednesday, I don't have no time. And over the weekend, all the spare time I had to work on stuff was spent on that, preparing for the hearing. I got no grading done over the weekend. Lots of work done on that other thing, but no grading. And then Monday and Wednesday of this week, again, full classes all the way. Tuesday, I thought I would have some time, but Tuesday morning was wiped out because that's when the hearing was. I was over on the Birmingham campus. Actually, before the hearing started, I got a couple papers graded because I had a few minutes in there that I could get some things done. But then, even then, I wound up advising students, okay? So I didn't have as much time to grade as I hoped I would. And then Tuesday afternoon, when I got back here and had the thing, then I had to start getting ready for Wednesday's classes because I hadn't got any of the physics tests or labs prepared. And by the time I got all those done, there was my office hours there too. I may have gotten a couple things graded, but that's all. So sorry that, so not only is, and actually some stuff may be graded, but I haven't been able to put it in Blackboard because I got to get the grading done first. So, sorry, that's my sad, sad story. Now, this is the last day of class, the day you've been dreading all term, I know, so get over it. But I want to make up as much time as I can from last time. Do you feel like you can stay? Okay, how long? Till about 11. Okay, we'll go till 11. I'll give you your test before you go, but you'll have to listen to YouTube to find out how far we actually got. And I'll state on there which questions are, would be bonus and which ones not, because I had to make out the test beforehand, not knowing how far we would get. Okay, so as I was starting to say before, we're in Chapter 4, that's Higher Order Equations, page 128, 4.1 Preliminary Theory Linear Equations. We're on example 10 on 128. Any questions before we get started there?
You passing out tests today?
Yeah, anytime you're ready to turn it in. Yeah. I'll give you the last test.
Is it online? Or
Oh, no, I'll give it to you today at the end of class or whenever you have to leave. And when is it due? I said this before, but I'll say it again. If you finish it and want to turn it in Monday, you can. Now, I'm in class basically all day Monday. What's that?
I have a class here Monday too.
Okay, well, if you are finished and want to turn it in, you can. In this room from 8 to 10:40, and then from 10:40 to 11, those 20 minutes, supposedly in the office eating lunch. I'd never get down there until about 5 or 10 minutes, grab a bite or two, and then get back for the next class. So I'm here from 11 till 1:40, and then I try to run back down and get another bite or two of lunch, and still I usually seldom get even 10 minutes there. And then I have a physics class that starts at 2 and goes until 5:30. However, because we will have a lab, but we'll have that earlier in the period, so I'll probably be finished with that class a little bit early. Okay, and then I'm have another physics class starting 5:30 and goes till 9, and again, that one will probably finish a little before 9. But if I'm in class and you don't want to wait on me and just want to slide it under my door, you know where my office is? Okay, you can do that and not have to worry with it. So either way you want to do with that, okay? If you are ready Monday. If you're not, technically it's not due until Tuesday, okay? So you can turn it in anytime Tuesday. But if you still are packed with time, you don't have enough time, anytime Wednesday and Thursday. I'd love to have it before noon on Thursday. I will take it on Thursday. But you see, even though we go back to 5-day work weeks on Friday of next week, I don't, because I have an infusion Friday morning first thing, so I have to be at the lab by 7 anyway, and so I won't be on campus at all on Friday. So I think the grades are due by noon on Friday, so I have to have grades in before I leave Thursday at 5:15. So I'd love to have everything in by noon on Thursday, if possible. But if you get it to me sooner, fantastic. Okay. Now, let me say this. Oh, yeah. Student course evaluations. Do you know about them? You do. Have you already done them?
No.
Okay. Well, you saw the email, though.
Yeah.
The link and everything. So please get those done anytime, but please don't forget to do them. We really value those. There's something else I was going to say. I don't remember what it is now. Okay. If I think of it, I'll say it. If not, hopefully it wasn't important. Okay. All right. Example 10, if there are no other questions. It says, by substitution, this function, oops, let me get my pen activated. Okay. By substitution, this function, y sub p, that's the particular solution, is equal to minus 11/12 minus 1/2 x. Really a fun-looking equation. Is readily shown to be a particular solution of this homogeneous equation. Y triple prime minus 6y double prime plus 11y prime minus 6y is equal to 0. Now it says it's readily shown. Well, let's readily show it, okay? How do we proceed with this? To show that is a solution for that. First step, take a derivative. Always a good yes, okay? Yp prime would be what? Pardon me? P. Yeah, y sub p, that's just a particular solution. What is its derivative? Negative 1/2. Okay, next. Yp double prime would be 0, as would Yp triple prime. Okay, let's see. Okay, this would be 0 minus 0 plus 11 times y prime, which would be negative 1/2, minus 6 times y, which would be a negative 11/12 minus 1/2 x. Okay? They claim that's equal to 0. I have my doubts. Okay? Zeros, that certainly doesn't bother us any. This will be minus 11/2 plus wait, I'm sorry. This is equal to 3x. I said it can't be equal to 0. Okay, it's equal to 3x. My eyes went down the line. Okay, equal to 3x. Equal to 3x. And let's do this one would be, ooh, the eraser didn't work. Okay, so 3x. Is that equal to 3x? Okay, this may be. Okay, now it won't if I can't multiply, if I can't write. Okay, that's minus 11/2, not 11/12. Okay, minus 11/2 minus 6 times a minus 11/12 would be plus 66/12, right? Okay? Plus 1/2 of 6, negative times negative is plus, 1/2 of 6 is 3x. x. So that part looks okay. Now what we have to do, does 66/12 reduce to negative 11, to 11 halves? Sure enough, 6 will go into 66. 11 will go, no, 6 will go into 66 11 times. 6 will go into 12 twice. Sure enough, minus 11 halves plus 11 halves, add to 0, 3x equals 3x. Yes, that is a solution. So to write the general solution, you also need the associated homogeneous equation. Okay, and the associated homogeneous equation is what my eyes landed on. So I'm going to delete all this because I don't have enough room. Okay, and the associated equation is your homogeneous equation. Okay, so that instead of the 3x, you put it equal to 0. Okay, now, oops, I didn't erase that. Okay, you put the 0 there. Now what you have to do is figure out the general solution for that equation, the associated equation. Okay, now what they tell you it is this, and it's called the complementary equation, by the way. That's what this stands for. Y sub c is equal to c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. Okay, that's what they claim. Let's see if that does work. What's yc prime? Pretty easy to do. c1 e to the x plus 2c2 e to the 2x plus 3c3 e to the 3x. Y double prime, yc double prime would be c1 e to the x plus 4c2 e to the 2x plus 9c3 e to the 3x. Y triple prime, yc triple prime is what? c1 e to the x plus 8c2 e to the 2x plus 27c3 e to the 3x. Now let's plug those into our differential equation and see what we get. Oh man, okay. Ooh, it's going to take a while. So it's going to be c1 e to the x plus 8c2 e to the 2x plus 27c3 e to the 3x. That's the y triple prime part. Minus 6 times y double prime, that would be minus 6 c1 e to the x minus 24 c2 e to the 2x minus 54 c3 e to the 3x. See what I'm doing? Minus 6 times y double prime plus 11 times y prime. So that's going to be plus 11 c1 e to the x plus 22 c2 e to the 2x plus 33 c3 e to the 3x. Minus 6 times y. Well, your yc here is, that would be a minus 6 c1 e to the 3x, e to the x. Why do I want to say 3 there? Okay. Plus 11 c2 e to the 2, I'm sorry, minus 11 Okay. Okay. Minus 11. C2E. No. It's a minus 6. Sorry about that. I was looking at the wrong line. Minus 6. C2 minus 6 C3 e to the 3x. Okay? Now, when you add all those together, we're supposed to get to 0. Reckon we will? Let's see. Here's a minus 6. Minus 6 is minus 12. 11 plus 1 plus 12. Those add to 0. Okay, over here you have a minus 24 and a minus 6. That's minus 30. Plus 22 plus 8. That's plus 30. Those add to 0. Here we have a plus 23 and a plus 27 and a plus 33. That adds to 60. Minus 54 minus 6. That adds to 60. Sure enough, all these are equal to 0. So that works. Okay? So we've gotten our particular solution, or they gave it to us. We showed it worked. Then we went to the homogeneous form, which is they call the associated homogeneous equation. You just took out the 3x at the end and put in a 0, and then they gave us a solution for that. That's now called the complementary solution. That's the particular solution. And we checked, and sure enough, those work. So now we know that the general solution for this, and I'll write it here, y, and we don't put anything else, just y is equal to the yc complementary solution plus yp, which is a particular solution. So that's going to be c1 e to the x plus c2 e to the 2x plus c3 e to the 3x minus 11 twelfths minus 1/2 x. Okay? There is your general solution for that original differential equation, which had a 3x right there. Okay? Now, the rest of this chapter is telling you how you came up with first well, you know how to get the, we'll do how to get the homogeneous solution, how to get the particular solution, then you put them together. The last theorem in this discussion will be useful in section 4.4 when we consider method for finding particular solutions, and that's the superposition principle. And I'll let you read it, and they do a little proof on it, pretty simple, just go through it. Let's do example 11, which uses it. I think that's usually more instructive than just reading the words. Okay? So let's see. You should verify that yp1, here's one particular solution, equal minus 4x squared. Okay? Is a particular solution of y double prime minus 3y prime plus 4y is equal to 16x squared, so minus 16x squared, plus 24x minus 8. Okay? Now, we need to show that is a particular solution for that. How do we go about doing it? Take your derivatives. Yp1 prime would be negative 8x, and yp1 double prime is equal to negative 8. So let's plug them in and see what we get. Negative 8, that's your y double prime, minus 3 times y prime, and that's going to be plus 24x. You see it? And then plus 4y, so that's going to be a minus 16 x squared. Is that equal to minus 16x squared? That part checks. Plus 24x. That part checks. Minus 8. That part checks. Yes, that's equal. So that was a particular solution. Okay? Verify this one. yp2 is equal to e to the 2x. Okay? Is that a particular solution to, y double prime minus 3y prime plus 4y? That looks familiar, doesn't it? But this time it's equal to 2e to the 2x. Okay? Again, how do we do this? How do we do it? Take our derivatives. yp2 prime is 2e to the 2x, and yp2 double prime is 4e to the 2x. So let's plug those in. 4e to the 2x minus 3 times 2 is 6e to the 2x plus 4 e to the 2x. Is that equal to 2e to the 2x? Well, let's see. Here we have 4 and 4 is 8, minus 6, sure enough, is 2e to the 2x. So, we found that yp2 is a particular solution for that same differential equation on the left, just a different thing on the right. Okay? See if we got room to do this one. yp3, particular solution 3, equal to xe to the x. Ugh. What are we going to have to do here? Product rule. And what would that give us? X e to the x plus e to the x. Very good. That wasn't bad. Let's do the yp3 prime, double prime. What will that be? It's going to be exactly, when you take the derivative of this, this first term, you're going to get the two terms. X e to the x plus e to the x. That's the derivative of the first term. Then the derivative of the second term is another e to the x, so that makes 2 of them, right? All right, let's plug, and show, I'm sorry, I jumped ahead. A particular solution to, I think you knew what was coming, y double prime minus 3y prime plus 4y. But this time it's equal to 2x e to the x minus e to the x. 2x e to the x minus e to the x. Okay, that's what we're gunning for here. Let's see if those derivatives will give us that answer on the right. So y double prime would be x e to the x plus 2e to the x minus 3 times y prime. That would be minus 3 x e to the x minus 3 e to the x plus 4 times y would be plus 4 x e to the x. The question, is that equal to 2e to the 2x e to the x minus e to the x? Let's see. Yuck. All right. Here we have a plus 1, x e to x, a minus 3. That'll give us a minus 2. Plus 4 would be a plus 2. So far, so good. 2x e to the x. Okay, that took care of those 3 terms. The 2 terms that remain is a 2e to the x minus 3e to the x. Sure enough, that's a minus e to the x. So sure enough, that is equal to that side. All right, that was fun. But what we can gain from that is that if your original differential equation had been this, and I'm going to have to take advantage of the space I've got, y double prime minus 3y prime plus 4y, that's been the left-hand side all along, is equal to the minus 16x squared plus 24x minus 8 plus 2e to the 2x minus 2x e to the x minus e to the x. If your particular solution was all that mess, I mean not your particular, your g of x was all that mess over there, but you know this particular solution satisfies the first one, this one satisfies actually the first three terms, this one satisfies the next term, and then this one satisfies the next two terms, then shoot, yeah. Now this isn't a general solution, but your y is equal to the sum of all those minus 4x squared plus e to the 2x plus 4 e no, plus x e to, I'm sorry, I got lost in the sauce here. Okay. 4 to e to the 2x. The pen won't come back on. 4 e to the 2x. This is the particular solution for that huge, humongous g of x here. That's the superposition principle. If you know that the pieces fit, then you know that you just add them together and those fit. Okay? So that'd be minus 4x squared plus e to the 2x plus, I'm sorry, I missed it again, x e to the x. I wrote the same thing, well, I wrote the wrong line down. Okay. X e to the x. This one, I was the line above it. Okay. All right. Then all you had to do was just find out the complementary solution. And they tell us that okay, well wait, not just that. You need that test. Oh, you got that finished. Okay. And wow. You're going to have to listen because we haven't even gotten to independent and dependent yet, so you may not be able to do any of number one. And we surely haven't gotten to undetermined coefficients of variation and parameters, so you have to listen. I don't think we're going to get there. You might be able to do one or more of the ones at the bottom, but you'll just have to listen and see. If it turns out that there's not enough worth it, then we may just say we'll go with those two tests. Would y'all be okay with that?
Yes.
Okay. Let's go as far as we can, though. So listen to YouTube and see what I say at the end here. Okay. Now, note that if you have these particular solutions, what you also have is that any linear combination of those particular solutions will do linear combinations of those g of x's. So if you multiply this term by some fixed constant, in fact it's already got a constant in it, for instance you could divide out an 8 and have a minus 2x squared plus 3x minus 1, then 1/3 of this minus 4/3 x squared will be a particular solution for that. Okay? When you look at the second, this one here, 2e to the 2x, if you divide by 2, then divide this by 2, 1/2 this. That would be a particular solution. Or multiply by 515.3, that would do it too. If you multiply that by it, multiply the particular solution by it. They're linearly related to each other. And this one, there's not much way to simplify that except multiply by something else. Give me a number. 2. So if this had been 4x e to the x minus 2x, then the particular solution would have been 2. If you double that, double this one. And then the linear combination, the combination of those will be for the whole thing. So that's how superposition works. Okay, then they have their remarks here. And again, we're looking at linear systems, so they talk about that. They talk about state variables. Those are the ones that you're going to be using to solve the system. And then the G's are sometimes called the input function or the forcing functions. And the solution is the output or response of the system. Just a little bit of nomenclature. Homework exercises here, 1 or 3 or both. Any of the, either 5 or 7 or both. Do 9. Do 11. Okay, yeah, do 11. Do 13. Those are all in 4.1.1. You should have already had those done. Then in 4.1.2, homogeneous equations, do any of the odds 15 through 21. Then do any of the odds 23 to 29. And then for non-homogeneous equations, the one we just did, do either 31 or 33, or both, and do 35. Okay? You can think through the discussion problems, but typically they don't have answers in the back. So, wow. This reduction of order, we really don't use, I don't think, that frequently. So I'm going to just sort of gloss over that one. And let's go to 4.3 with your homogeneous linear equations with constant coefficients. Okay? That is something you do use a lot. Okay? Now, let's get down to a second order equation, what they're calling the auxiliary equation here. Okay? I'm going to clear my slide here. And what if you had this? AY double prime plus BY prime plus CY equals 0. Okay? Where A, B, and C are constants. Okay? If this is the form you have, and you have linear equations and y and its derivatives. Okay, now again, what does that mean? The y can't be squared or to the 1/2 or to any other power. The y primes can't be squared or to the 3/2 or negative 1/2 power. The y double primes can't be squared, cubed, or anything other than the first power. Okay? That makes this linear. Okay? Second order equation, but still linear. Okay? And A, B, and C are constants, not functions. Not A of x, B of y, B of x, and C of x. They're constants. If you have that as the situation, here is the form we always try first. Y is equal to E to the mx. When you have that form, that very simple form here, this is what we try as a solution. Okay? Well, if that's your y, what you do next? Take a derivative. Y prime would be m e to the mx, and y double prime would be m squared e to the mx. Okay? Now notice that equation has to equal 0. That's why these are called homogeneous. Not homogeneous like we did before when they were at the same powers, but homogeneous because it's equal to 0. Okay? So let's plug in what we've got. A m squared e to the mx, right? Plus b m e to the mx plus c e to the mx, that's equal to 0. All right? If that's a solution, and those are the derivatives of that solution, when you plug them in, this is what you get. Now, what's the good news here? What you notice is in every term. E to the mx. So let's factor it out, right? So that'll be e to the mx times am squared plus bm plus c, and that's equal to 0. Well, guess what? E to the mx, that's an x, not a v, is never equal to 0. It can't be. E to the mx looks like this. If m is positive, it looks like that. If m is negative, it looks like that. Oops, it doesn't cross there. But you get the general idea, okay? Can never equal 0. If it's a minus e to the m, it looks like this. If it's minus minus, it looks like that, okay? It never equals 0, okay? That's the point. So therefore, we can divide it away, okay? And what are we left with? am squared plus bm plus c equals 0. Guess what that is? A good old quadratic equation. And guess what we can do? We can solve that any way we can solve quadratic equations. And how is that? We could factor it if it's factorable and get solutions for m, or we can if we can't factor it, quadratic formula and get solutions for m. Even if they're complex solutions, we can get those. So sure, we can come up with an answer there, okay? And this right here is called our auxiliary equation. And after a while, as soon as you see it's in this form, you can go straight to that auxiliary equation. Because you don't need to mess around with the e to the mx anymore. They disappear. Okay? Now, here are some possibilities you get with that. Now, do you have a book? Yeah, okay. Here are the possibilities with that. When you factor, if it's factorable, you'll get 2 m's. Possibly. Or you'll get 1 m. Then it's a repeated root. Or you get no m's in the real number system, and then you'll have imaginary roots. Okay? Or, if you do quadratic formula, you get the same thing. Remember that discriminant you have at the end of a quadratic formula? What's under the radical? B squared minus 4ac. Okay? If that turns out being a positive number that you can take a square root of, and it happens to be a perfect square, that means you could have factored the thing to begin with, okay? You'll go and get real solutions. 2, not just real solutions, 2 integral solutions, okay? No, not integral. Rational solutions, okay? If, however, that b squared minus 4ac is positive, but not a perfect square, then you'll get 2 irrational solutions. One's a plus and one's a minus, okay? Now, if that b squared minus 4ac turns out being 0, that means you have one repeated solution, okay? And if that b squared minus 4ac turns out being negative, that means you have two complex solutions, okay? So, it all depends on that determinant. Yeah, they call it a determinant. Not the same determinant you use in matrices, okay? All right. Now, let's look at these three cases that we would have. In that first case where you have real solutions, they could be rational or they could be irrational, but two real solutions, then your solution would be y is equal to c1 e to the m1 x plus c2 e to the m2 x. If m1 and m2 are real, that's what you got. Pretty straightforward. Okay? Now, if on the other hand, if m1 is your only solution and it's a repeated solution or repeated root, then your y is equal to c1 e to the mx, or m1x, whatever you want to call it. But that's your only one. Then your second one is plus x, c2 x e to the m1x. Okay? That's how we come up with two parameter system when you only have one real root. Okay? Now, in the third case, and you will occasionally hit this, where your M1 and M2 come up being complex. Okay? That means they're of the form, let me make sure I write it the same way they do, A plus IB. Okay. They'll always be in the form, your M1 will be alpha plus I beta, and your M2 is always going to be, now, time out. Let's go back. Remember, your A, B, and C are constants. They didn't say integers. They didn't say rational numbers. They could be irrational numbers, but they're real. They're real, not complex. Now, as long as those are real numbers, A, B, and C are real numbers, and you come up with a complex solution, both of those are going to be complex, and they're going to be complex conjugates of each other. The second one would be alpha minus IB. Okay, I think they say BI. No, they say I beta. Okay. All right. Now, if that's the case, I'm going to need some more room. So I'm going to start at the top and erase some of this. We know what those form is. I've already harped on that. Okay? And we know what our solution is. Y is equal to e to the mx. I hope you remember that. Okay? That's where we all started. Okay? And we got to this form and we factored it out. And we got to our auxiliary equation. So I think I'll erase everything down to the auxiliary equation. But this time, you wound up with that discriminant being, not determinant, discriminant. The discriminant wound up being negative. So now you have complex solutions. So that's what I'm going to do at the top now. So the y is equal to C1 they write it this way first. E to the alpha plus I beta x, that was what your M1 was, plus C2 e to the alpha minus I beta x. There's your solution. Isn't that messy? Totally messy. Okay? Now, in practice, we prefer to work with real functions, yes, okay, instead of complex functions. To that end, we use Euler's formula. I don't know if you remember it, but here's Euler's formula. E to the I theta is equal to cosine theta plus I sine theta. Okay? That's one of Euler's many contributions to really complex stuff. Now, the theta is a real number. Okay? So you haven't gotten rid of the i's yet. You still have an I in there, but at least your variable, okay, is a real number. Okay? Now, so if we're doing this, let me rewrite this solution using the rules for exponent. C1 e to the alpha e to the I beta, that's alpha x, e to the I beta x, plus C2 e to the alpha x e to the minus I beta x. Right? Now, instead of this e to the I beta x, we're going to put these forms. So this will be C1 e to the alpha x, and instead of e to the I beta x, we're going to put cosine beta x plus I sine beta x. Okay? Now, that may not look a whole lot better, but it feels a little better anyway. Okay? Slightly better. Okay? Now, okay. Wait, okay, that's just the first part of it. Then plus C2 e to the alpha x times, and then e to the minus I beta x is going to be cosine beta x minus I sine beta x. Okay. Now, I hope you don't feel like I pulled something over on you there, because this only showed e to the plus alpha. If you put a minus here, that would put, you're only negating the minus there. No, okay, you're negating the theta too. But cosine of negative theta is the same as cosine of theta. That's an even function. So that's why we leave the plus there. But then the sine of negative beta x is minus the sine of beta x, so that's why we could put that. Now, here, well, it's not quite good news yet. Okay. Okay. They do something I find a little disconcerting here. because I don't quite. It says, note that by first adding and subtracting the two equations in 7, before you put them in with the constants, then if you add these two together, you get 2 cosine beta x, okay? And you get oh, I messed up here. Oh, yeah. If you add the two together, you get that. If you subtract the two from each other, then you get, if you do e to the I beta x minus e to the I minus I beta x. Okay, if you did that, then the cosines subtract out, and you're left with 2I sine beta x. Okay, now, they say if this is true for any constants, then make it so these c's up here, make it this way, okay? C1 and C2 are 1, and then later do C1, 1, but C2 minus 1 in turn, and you come up with two solutions. And because we just don't have that much time, here's our final answer. Y, or space either, is equal to the C1 e to the alpha x. You see, we got that from right here. That term right there is going to come through for us. Okay? Cosine beta x, and that's that term. In fact, cosine beta x, that's when you combine those two together. E is equal to C1 e to the alpha x cosine beta x. Done. Plus C2 e to the alpha x cosine yeah, I'm sorry. Okay, that should be a sine beta x there. Sine beta x. Okay, which then you can factor out this e to the alpha x and leave you C1 cosine beta x plus C2 sine beta x. Okay. Now, they skipped, I think, way too many steps there. They do show some stuff at the bottom that's supposed to justify it. The bottom line, though, is here is your solution. Okay? There it is. Y is equal to e to the alpha x plus times C1 cosine beta x plus C2 sine beta x. The good news here, all the i's are gone. So even though your M1 and M2 were complex, your solutions are not complex. They are real solutions. Your alpha shows up just with the e to the alpha x, that's the real part, and then the complex parts show up C1, that's where your constants go to, cosine beta x, C2 sine beta x. So those have real solutions, okay? So, believe it or not, we're well on the way to solve some second order differential equations. So let's do it right now. Going to start with example 1 here. My head is clogging up on me. Do you mind if I take a quick break, run down to the restroom? So I'm going to put this. Okay. So it says solve the following differential equations. 2y double prime minus 5y prime minus 3y is equal to 0. What's your first step? Say again? What are you going to take a derivative of?
Oh, you're right.
Yeah. Huh? Now again, let's know what form we have. We have linear second order differential equations with constant coefficients. Say again? Yeah, y is equal to e to the mx. There's going to be our fallback. We love e's, right? They take derivatives so nicely and everything. So now we do what? That we have that. Yeah, y prime would be m e to the mx, and y double prime is equal to m squared e to the mx. Now after a while, you may be able to skip this step if you're familiar with it, but it's not bad to do it at first. So now we have 2m squared e to the mx minus 5m e to the mx minus 3 e to the mx, supposedly equal to 0. And what can we factor out? E to the mx, just throw it away, okay? Divide it out, whatever you think. That gives what we call our auxiliary equation, 2m squared minus 5m minus 3 equals 0. Now, what might we try first? Factoring, okay? And if this is indeed factorable, what was the only possible factorization of 2m squared? Say again? I can't hear. Okay. Okay, m squared, I said m, I wrote m squared, okay. M times, factor 2m squared. M times 2m, right? Only possible factorization of that, okay? Then next we look at the sign of the last term. That's a minus. What does that tell you about these two signs? 1 plus and 1 minus. Let's just put plus and minus. May or may not work. What's the only possible factorization for 3? 1 and 3. Let's try it. 1 and 3. All right, let's FOIL it and see if we got the right one. M times 2m is 2m squared. Yes. M times minus 3 would be minus 3m plus 2m would be minus m. Wrong number. So therefore, let's change numbers. Okay? So let's swap our 3 and our 1. Okay? And put the 3 here and the 1 there. Now let's see if that works. M times 2m is 2m squared. Yes, still works. Minus m plus 6m. What does that give us? Minus m plus 6m plus 5m. But this time we got the right number, just the wrong signs. So therefore, change the signs. Okay? So we'll make this the plus and make this one the minus. Okay? Now let's see if we got it to work. M times 2m is 2m squared. Yes. M minus 6m is minus 5m minus 3. Yes, we got it. So what does this tell us? m is equal to 3, or negative 1/2. So here are our two solutions. Y is equal to C1. Remember, these are general solutions. We don't have initial values, so these are arbitrary coefficients. C1 e to the, this is where we go back here, C1 e to the 3x plus C2 e to the minus 1/2 x. There's your solution. Done. Huh? No. And if you wanted to check it, go back and plug in and see what you get, but sure enough, it should work. Okay? No, it's not bad at all. So we get y is equal to C1. They put the e to the minus x over 2 first, plus C2 e to the 3x. It doesn't matter which one you put where. All right. Let's do the second one. I think I'm going to need to erase this. I took more room than I probably should have. Let's do B. Y double prime minus 10y prime plus 25y is equal to 0. Where do you begin? Oh, I messed something up. This is a y here. Say again.
Y squared, y double prime would be m squared.
Okay.
Oh, we gotta do e to the m.
Okay. Now, if you want to, no, you're absolutely right. If you want to skip that, but I still think it's a good idea to write it down. Y is equal to e to the mx. That's what we're assuming. Now, if you want to go straight to your auxiliary equation, I think that's a great idea. So what would that be?
M squared.
M squared
Minus
minus
10
10m
plus
plus 25 is equal to 0. Perfectly fine. As long as those are linear, second order, differential equation, constant coefficients, you can do exactly that. That is your proposed solution, okay? And now what? Second? Factor. Okay, let's see if we can factor it. Okay, only possible factorization for m squared. M times m. Okay, you look at the sign of the last term. What is it? It's a plus, and that means these two signs have to be both, they have to be the same. Look at the middle term, they're both negative. And then what will it be? 5 and 5. You're absolutely right. Or you could, when you first looked at that, say, oh, it's a perfect square trinomial. Okay? So this is going to be m is equal to 5. Well, what do we do if we only have one solution? Y is equal to, if you want to, you can look back at, see the case 2 on the previous page, page 136. Y is equal to C1 e to the 5x plus C2 x e to the 5x. There's your solution. Done. Right? All right. And that's exactly what they got in the book. Now we may have enough room to do the C one here. The C one is y double prime plus 4y prime plus 7y is equal to 0. And where do you go from here? Y is equal to e to the mx because that's a linear differential equation with constant coefficients, okay? So, you want to go straight to your, okay, and what would that be? So I got m squared
plus 4 plus
Okay? Let's try factoring. That'll be m times m. Wait, signs are? Second? Plus, yes, exactly. They have to be the same because this one's positive, and because that one's positive, both have to be positive. Now, can you think of any factorization for? No, you can't. Okay, so if you can't factor it, what do we try next? It's what? Not yet. We've got to do something to it first. Second? Quadratic formula, exactly. Exactly. How does that go? M is equal to remember it? Okay. Here's how it goes. Well, I'll write it here. M is equal to minus B plus or minus the square root of B squared minus 4AC divided by 2A. Okay. Okay. Now, the question is, what in the world are those A's, B's, and C's? Negative 4 plus or minus the square root of, which is 16, minus. Now, here's what I do next, okay? I count my minus signs. The minus 4 is always a minus sign. Your A is positive, your C is positive, you have one minus sign. That means that this is going to be a minus. So then you just multiply those three numbers together. 4 times 1 is 4, times 7 is 28. Looks like a big boo hiss coming, doesn't it? And what do you got down here? Two times 1 is 2. Okay. Now, minus 4 plus or minus the square root of sort of like 12, negative 12. Okay. Over 2, which is going to be minus 4 plus or minus. Now, do you see any perfect squares hiding? Well, wait. You got an I there. The minus 1 comes out because square root of minus 1 is I. That comes out. And that leaves you a 12. Any perfect squares in there? What? What's the square root of 4? 2. So it's 2I. And then what have you got left? Square root of 3. Right. Okay, because it was a 12. 4 times 3 is 12. So that's what we've got over 2. But now the good news is the 2 goes out. That 2 goes into that twice and goes into that once. So our answer is minus 2 plus or minus I root 3. Okay? All right. And I think this book, well, no. This book writes root 3I. I do not like that. I know you're supposed to write, yeah, because then it may, if you extend that radical a little too far, you might say, is that I under the radical or not? You know, if you put it in front, it's obviously not under the radical.
Make it look like that is root 3I.
Yeah. So I don't like to put the I afterwards, even though technically it's A plus BI, but just to keep from getting myself confused. Now we're in a funk here. What do we do here? Now we can go to a case. Say again? Yeah, and this is case 3. So y is equal to C1. Now let's see. I think they actually, before they even do the C's, okay, and this should be, I mean, I like to think of it this way. Here's my real part, okay? And these, by the way, this is, so M1 is equal to minus 2 plus I root 3, and M2 is equal to minus 2 minus I root 3. You don't have to do that, but if it helps you, you gotta do it, okay? Now, in fact, it may not help at all. But the real part of that is minus 2, right? Okay? Well, the real part, that would then be e to the minus 2x. That comes out front. That is your alpha here, is the minus 2. So you see the case 3, which is just above there, the blueprint there, there's your final solution here, okay? So pull out the e to the alpha x, that's e to the minus 2x, and then write the rest of it down. C1 cosine, now what's your beta x? What's your beta here? Okay, yeah. The I is I part, the beta is, this is plus or minus beta I, okay? So the beta is root 3. So that'll be root 3x plus C2 sine root 3x. There's your solution. E to the minus 2x, there's your alpha. C1 cosine root 3x. And even there, I am really tempted to put x root 3, but I think I can clear that, make that pretty obvious. Plus C2 sine of root 3x. There you have it. Now, let's go to initial value problem. Okay? You said you're good till 11, right? Okay, good. We'll go for that. Here's another one. 4y double prime plus 4y prime plus 17y is equal to 0. Given that y of 0, initial condition, is equal to minus 1, and y prime of 0, same initial value, is equal to 2. Okay. Where would you begin? Second. Okay. M squared equals 0. Okay. Okay. Second. Here. What's that?
I was going to ask, could we go straight to plugging in?
Straight to what?
Plugging in.
No, not yet.
But that can't be.
It cannot be factored.
Yeah.
17 is a prime number, so it's only factorization 17 and 1. There's no way, you could do a 4 or 2, anything times 17 and times a 1 and come up with a 4. Okay? It's not going to happen. So we go straight to, which is, okay, which in this case is negative 4, plus or minus the square root of, which is 16, minus 4 times 17. Okay, I think I can already smell a big blue hiss. What's coming up next? Over 8. Very good, 2a. Good deal. And this is going to be minus 4 plus or minus the square root of 16 minus 16 times 7. I'm just going to leave it at 16 times 17. Is that okay? No. Watch this. Okay? Now, isn't that minus 4 plus or minus the square? Okay. Factor out of 16. Square root of 16 is 4. Right? What do you have left? The square root of 1 minus 17, which is minus 16. Right? Okay? Am I doing that right? It seems just way too... I think it does work.
So we just take the root of that 16.
Okay, over 8, and this will be minus 4 plus or minus, and okay, I want you to do that on your calculator now. I'm beginning to doubt it. 16 minus 16 times 17. Okay. Do the square root of that. I'm getting it's a perfect square, is it? Huh? Yep, and that's exactly what we got. 16i. Okay, so we could have factored it. Sorry about that. I never would have guessed it. Okay? Well, not well. Okay. Over 8. So what does this give us? Negative 1/2 plus or minus 2i. Okay. That's what your m is. Your m's are, really. Okay? So I think we can go right to writing down a solution now, can't we? Y is equal to e to the minus x over 2, negative 1/2 x, right? Times C1, we're still going to do it this way. C1 second cosine of 2x plus C2 sine of 2x. There's our general solution. But we have boundary conditions, or initial conditions. So when x is equal to 0, y is equal to minus 1. And when you plug in a 0 for x, what's e to the negative 0 over 2? 1. Okay, so that's just a 1. And you have C1 and C1 cosine of 0 is 1, right? Okay, plus C2 times the sine of 0. Sine of 0 is 0. Okay, so this just gives us that C1 is equal to negative 1. Okay, that gives you 1. Let's do our y prime. Okay, because we got to do that. And here we got a fun little product rule. And what do we get here? Yeah, it's a product, so you do it any order you want to. You want to start with that derivative? Okay. Chain rule it. Okay. 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 Tell me how you're doing your product rule.
I was doing it like as e to the negative b, e to the negative x. I think I wasn't doing chain rule. I think I was just doing the product rule.
Okay, how does that go?
But I was doing it with like that. I was doing it like e to the negative x over 2,
Right.
and then the next.
Okay, and then the next part you're going to do what? See, if you use this, then you take the derivative of that.
Yeah.
Is that what you were doing?
Yeah.
Oh, okay, yeah. Well, then you're right. Okay, I thought you said take the derivative of that. Sorry, I misunderstood. Okay. So e to the, okay, you did the first times the derivative of the second. Okay, and what is the derivative of the second? Okay, C1's in there. Negative sign, so the negative sign's in there. Sine of 2x and a 2. Yeah, because of the chain rule of that. Okay? Plus 2c2 cosine 2x. Okay. Plus, actually not plus, it will be a minus ultimately because when you take the derivative of this, you're going with a minus there. So minus 1 over 2 e to the minus x over 2 times this. C2 cosine 2x plus c, that's C1 cosine 2x plus C2 sine 2x. Okay, now pause just a moment here and let's fix something. We already know what C1 is. It's a negative 1. So let's take that out of the picture here. Okay, so that's going to be a negative 1 times a negative 2 is going to be a plus 2. Okay, C2 stays in there, and the C1 here becomes a negative 1. So that's going to just be a minus there. Okay. Got it? Now that's what y prime is. What we're interested in is y prime at 0. And y prime at 0 is going to be 2 when we plug a 0 in here. What will this give us? 1. Okay. And this gives us a, when you plug in a 0 for x, sine of 0 is 0, so that doesn't give us anything. And here we get a 2 C2, yeah, cosine of 0 is 1. So C2, 2C2, so 2 is equal to 2C2. I really don't need that parentheses there. That's all you get from this one, minus 1/2 times 1, right? Right? Times a minus 1, because cosine of 0 is 1, and then sine of 0 is that. So that's what we got. So what we got, 2 is equal to 2C2 plus 1/2. Okay, so let's subtract 1/2 from both sides. Get out of there. Okay. Okay. So that is going to give us, sorry I'm running out of room at the bottom, that's going to give us 3/2 is equal to 2C2, divide by 2, and you get 3/4. C2 is equal to 3/4. Now, let's go back and plug in. Y is equal to e to the minus x over 2 times minus cosine 2x plus 3/4 sine of 2x. Unless I made some dumb math errors, I think that's what we've got. Let's see. E to the minus, where was it? I just wrote it down. There it is. E to the minus x over 2 times minus cosine 2x plus 3/4 sine 2x. Done. Now, all right. I think we got that one. Now, they say 2 equations worth knowing. Okay? Let's write these down because we want to be worth knowing them. Okay? If this was your one, y double prime plus k squared y is equal to 0. And the other one is y double prime minus k squared y equals 0. Okay? All right. The first one there basically always comes out this. I don't know why they don't put these in blue, but they didn't. This one has a solution of y is equal to c1 cosine kx plus c2 sine kx. Okay? And if you think about that for just a moment, I think you'll see why that's true. Because the first derivative here, right, will be a minus c1 minus k c1 sine kx, right? And this will be a plus k c2 cosine kx, right? Then when you take the next derivative, this will be a c1 k squared minus c1 k squared cosine kx, and this will be a minus k squared c2 sine kx. And sure enough, when you do the second derivative, add it to k squared times the first derivative, it comes out to be 0. Because the second derivatives of those, that's cyclic. Okay. Now this one over here, they like to go to hyperbolic sines and cosines, which are perfectly fine, but I've never really used those to speak of, except in calculus classes and stuff like that. I would stay with the e to the mx. I would just stay with that because that's going to give you exactly what you get with a hyperbolic. It's just that hyperbolic is just a name for a special set of e to the. It's e to the mx plus e to the minus mx, basically, is what you get. And it works. And you got over 2 in there, but it's to me, it's so much easier to use than hyperbolic. So use them whichever way you want. You can always start with your e to the mx, and you see it's going to work out. Okay. Now let's go to higher order equations. Okay. And I think you'll see, just carries on, extension of what we just did. We're going to start with constant coefficients, okay? And when you do your m's, you know, your m equation, your auxiliary equation with m's, you're now going to have cubes in there, okay? Well, you still try to factor if you can factor. You do all the things for finding roots that you did back in pre-calculus algebra. Did you have pre-calculus algebra? Okay, yeah. Remember when you use rational zeros test, you know, and Descartes' rule of signs, and all the tools you used before to get roots still usable. That's all you're doing. Okay? Sorry. However, as you go to higher orders of powers, you may wind up with higher orders of multiplicity. And if you do, then the first one is going to be an e to the m1x, or mix, they call it. I think I can't read the number there. And then if you have higher degrees of multiplicity, for every degree of multiplicity, add another x. X e to the m1x, x squared e to the m1x, all the way up until you get to x to the k minus 1 m1x, or whatever that is. Okay? And then you also have linear combinations of solutions as well. Okay? You remember you could have real coefficients, you have complex coefficients. If you have complex coefficient, as long as those constants were real numbers, then the complex will always show up as ordered as complex conjugates of each other, so you can use your sine and cosine just like you did before. All right, so let's do example 3. Solve this one. Y triple prime plus 3y double prime minus 4y is equal to 0. mx. Perfect. Okay? Three, yeah. You're getting me to do it too, aren't you? Okay. All right. 4 minus 4 is equal to 0. A big boo hiss there, isn't it? Okay. All right. Frankly, I would try rational zeros test. Okay, do you remember how that goes? You're looking for rationals in the form of P over Q. P and Q are integers, where the P are all the potential factors of 4, which is plus or minus 1, plus or minus 2, and plus or minus 4, over the rational derivatives of your first term, which is 1. That's just plus or minus 1. Well, goodness, if you divide plus or minus, you just have those. So there are 3 possibilities. 6 possibilities. Plus or minus 1, plus or minus 2, plus or minus 4. Now, the easiest one to do is the plus 1. Because then, if you plug that in, you just add your coefficients. Right? And what do you get? 0. So 1 is a solution. Well, now you still got to do synthetic division with it, so let's do it. 1, you know, is going to be a solution. You remember how to do synthetic division? Okay, you do the coefficients. 1, 3, 0, negative 4. Why? You have to account for every term. You're missing M. Yeah, so the 0, okay. You always have to have one more digit here than you have maximum exponent there. So you have a 3 there, you need 4 digits there. Put that 0 in for the missing term. Okay? Then my little rule, I've never seen it in a book, skip a line, draw a line. That's pretty nice, okay? Then bring down the 1, and then you multiply 1, and add 4, multiply, add. You're stuck in the rut, aren't you? Multiply.
4.
All right. Add 0. Ding, ding, ding. That's what we wanted. We knew it was going to be because it worked before. So what we have left here is what? Okay, but you get it back in with m's in there. You drop the degree by 1, so this will be m squared plus 4m plus 4 equals 0. That's a quadratic. We can deal with that. In fact, I think you can probably see what you got now. What, can't you? What you got? Plus what? Not minus. Yeah, times another m plus 2. All right, now let's check it and make sure. M times m is m squared plus 2m plus 2m is plus 4m plus 4. Yes, that works. So this is a repeated root, right? Repeated 0. We had 1. Oh yeah, wait, let's make sure we get this. M is equal to 1. And here we have m is equal to 2 with a repeated one. Okay? So what's going to be our solution then? Can we write it yet? Okay, let's first with this one, to the x, okay? Plus C2 e to the 2x, and then what do we do for our next one when you have a repeated root? That was case 2. It's C3 x e to the 2x. Remember that? When you have a repeated root, there's case 2 repeated real roots. The first one is m1, and the second one is e to the m1. Next one is x times e to the m1. So there we have it. You can plug that back into C. Let's see what they got. Oh, here we go. Y is equal to C1 e to the x plus C2 e to the... Oh, my goodness gracious. I got going too fast. Your m is equal to minus 2. That's your repeated root, right? Yeah, so this should be a minus 2x. And sorry about that. That's a pretty ugly minus sign. Okay. Minus. Sorry about that. Get to going too fast. Okay? Which I'll never do, really. Okay. All right. How about a fourth order differential equation? That third was so much fun. Okay. By the way, each order is going to give us another arbitrary coefficient. Okay. Fourth order. Oh, why did you? Well, I think I know why they did. d4y dx to the fourth plus 2 d2y dx squared plus y is equal to 1. Okay? Okay, that's where we're going to start anyway. And then what do you get next?
L to the
m fourth m squared equal, oops, this is a 0 there, not a 1, okay, is equal to 0, okay? What's that? Okay, actually, that's the perfect square itself, isn't it? Yeah, but skip both the 3's and the 1's. You have all even, so this would be m squared plus 1 squared. Do you buy that? Okay, let's try it. Square the first, that's m fourth. Twice the product, that's that. Square the last, yes, that's right. Okay, and that's equal to 0. Which then leads us to, you got m squared plus 1 is equal to 0. What do you reckon m could be? Second? Y, sorry, m. Okay. M is equal to, well, let's just do it this way. M squared is equal to -1, right? So m is equal to plus or minus the square root of -1, right? And what is that? Yeah, plus or minus I. Okay? But it's a repeated root, so we're going to have whatever we get here, then we're going to multiply x in front of it and do that too. Except this is going to be 1. And by the way, your a here, your real part, is 0. You don't have a real part here. All you have is an imaginary part, right? So, what you reckon that will look like? Second? Yeah, but you don't have an E. You don't have, there's no alpha in this one. It's only beta. So it would be e to the 0 m, which would be 1. So it's not there. Okay? The beta, though, is a -1, or is a plus or minus 1. So that would be C1 cosine x plus C2 sine x, right? The beta is 1. And then, because this is a repeated root, then you do plus C3 x cosine x. That's what you do with a repeated root, remember? Plus C4. What's that? Yeah, right, yeah. C4x sine x. Now, I don't know if they did them in the same order, but that's my guess. Let's see what we've got here. C1 cosine x plus C2 sine x plus C3 x cosine x plus C4 x sine x. Yes. Okay. Now, all right. I'm trying to see what they're saying at the end. We conclude with the aid of Euler's formula, the general solution of the corresponding differential equations must then contain I've left off the first part. Example 4 that we just did illustrates a special case when the auxiliary equation has repeated complex roots. In general, if M1 is equal to alpha plus I beta, beta greater than 0, beta positive, is a complex root of multiplicity k of an auxiliary equation with real coefficients, then the conjugate M2 is equal to alpha minus I beta, also a root of multiplicity k. From the 2k complex variable solution, you have e to the alpha plus I beta x, e to the alpha minus I beta x, e to the x, e to the, so you have this. We conclude with the aid of Euler's formula that the general solution of a corresponding differential equation must then contain a linear combination of the 2k real linearly independent solutions basically it's saying the same thing we just did. Now, if you have rational roots, of course the most difficult aspect of solving constant coefficient differential equations, finding the roots of auxiliary equations of degree greater than 2. Sometimes we can try to test the auxiliary equation for rational roots. That's what we did. Recall in the earlier one, recall from pre-calculus that if M1, is that 1 or I? I think it's a 1. M1 is P over Q, rational roots. So yeah, that's what. We've already done that, so that's nothing new. Okay, so let's do example 5, which I think we'll be doing it again. Okay? So, okay. 3y triple prime plus 5y double prime plus 10y prime minus 4y is equal to 0. What you got? Say again. E to the mx. Okay, that's where we're going to start. And our auxiliary equation will be 3 cubed okay. Now, when I have one like this, the first thing I do before I do rational zeros is see if we can do factor by grouping, because this is a 4-term polynomial. That works whenever you have even number of terms. A 3-term, a 5-term don't even bother. So this is a 4-term, so let's look. If we group these two together, we're going to wind up with an m squared times 3m plus 5. No, not going to work. Okay? Worth a shot to see if factoring by grouping will help. This one will not. Most of the time it won't, by the way. But it's worth a shot. So our next help is what? Yeah, rational zeros test, and that would be P over Q, where P over Q is some combination of The P is all the possible factorizations of 4, which would be plus or minus 1, plus or minus 2, plus or minus 4. And the Q is all the possible factorizations of 3, which is plus or minus 1, plus or minus 3. And that's all, folks. So let's write them out. Well, I like to do the whole numbers first. So that's plus or minus 1, plus or minus 2, plus or minus 4. Then do the fractions. Plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. Now remember, we will only have, at most, 3 zeros. So we got 2, 4, 6, 8, 10, 12 to choose from. We're not going to do them all. We're just going to stop when we get 3. What's the easiest one to do? 1. And I can just look at that and say, 1 ain't going to work, okay? Because if you put in a 1, you get big number plus small negative. So 1's not going to work, so don't even mess with 1. The rest of them we'll do by synthetic division. And frankly, I like minus 1, so let's do that. And what will be our coefficients here? 3. Okay, you need 1 more than your maximum term. You got it. Now we do what? Skip a line, draw a line. Bring down the 3. That will give us negative 3, 2, negative 2, 8, and then, right? And then a negative 8. That's not going to work. But I still want to look at that, negative 8 and 4, that'd be negative 12. Now, the reason I want to look at that, there is another rule, it's the upper bound and lower bounds. This doesn't fit either one, so we're not going to mess with it. So negative 1 is not a root either. What you want to try next?
How about negative 2? Because it got to be a negative, right?
You don't know that for sure. I mean, yeah, but if there's a negative, it's got to be a positive too, you know, because if they're all negative, well, they could be all negative. So it's either 2 or negative 2, I don't care. Which you want? 2. Let's try 2 first, okay? I've already brought down the 3, that would be, of us, a 6. Oh, I thought you said 2. Did you say negative 2? Oh, we already did negative 1.
No, I said
2,
2.
okay. 2 times 3 is 6. We add, yeah.
I was subtracting right there, that's why I kept saying negative.
Okay.
11.
11, 22, 32. Now, I did all those even though I knew it was going to give me a 0. If you put a positive in here, and all the signs of this are going to be positive, you can't go any higher. So that means we're going to throw out the plus 4. No reason to even try. Okay? Because this is an upper bound. May not be the greatest upper bound, but it is an upper bound. So we're going to not mess with the 4. So I said eliminate what you can. So the plus 4 is out. Okay? Plus and minus 1's out, and now we got plus 2's out, and we also got rid of plus 4. Okay? So what do you want to try next? Negative 2. Okay. All right. All right, and what will that give us? Negative 6. Negative 1. 2. 12. Negative 24. Negative 28. Okay. Now, if this one's a negative, and you alternate signs down here, that means that's a lower bound. So, Negative 2's out, but also is negative 4. So we don't even have to try that. Okay, so negative 2's out, and negative 4's out too. So we're going to have to go with our fractions. Okay, we love our fractions though, don't we? Okay, sure we do. All right, so let's see what we get. Which one you want to do first? 1/3? Okay, why not? Okay, do that. Second. 1. 6. 1/3 times 6 is 2. 12. 4. 0. Ding, 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 ding. We got a winner. A winner. Okay. And what's more, okay, we are down to a quadratic now, which is rather bizarre. Yeah, no, it's fine. Okay. So we do know that m equal 1/3 is a possibility. Now we write down, anytime you get down to 3 here, write it down as 3m squared plus 6m plus 12 is equal to 0. And what's one thing you note about that one? A 3. Okay? And when you do, divide it out. That will go, that will be a 2, and that will be a 4. So you got m squared plus 2m plus 4 equals 0. Want to try to factor that? Good luck. No. It can't. Okay? So if you can't factor, where do we go next? Okay, and what would that be? M is equal to negative what? 2. Negative 2 plus or minus the square root of 4 minus 4 times 1 times 4 over 2. Okay? And this will be negative 2 plus or minus the square root of, that would be 4 minus 16, which is negative 12. Huh? Negative 12 over 2. Okay? So that will be a minus 2 plus or minus. I'm going to pull out the square root of negative 1, which is an I. And that leaves us in there what? Okay, 4 times 3, the square root of 4 is 2, so that brings out, and you're left with a root 3. Okay? Over 2, and that divides out the 2's. Okay? So our final answer is m is equal to minus 1 plus or minus I root 3. Okay? Now we can do you feel confident doing the solution from now, or you want to do it in pieces? Second? Okay. Yeah, well, yeah, we're going to use x's because those are your, that's what we assumed the answer was in x's, but it could be thetas, but, so let's start with the one we know. M is equal to 1/3, so that's y is equal to c1 e to the x over 3. That's that first one. Plus, now, we do that part. Remember how that went? That is the real part of this thing. So that would just be e to the minus x times, that's your alpha part. The alpha is minus 1. E to the alpha x times, then C2, second, cosine of root 3x, or theta if you want to do all thetas, you know, plus C3 sine of root 3x. Okay, there's your solution. Okay, weird e there. Let's see what we got. Y is equal to C1 e to the x over 3, good for them, plus e to the minus x, that's their alpha x, e to the alpha x, times, open parentheses, C2 cosine root 3x plus C3 sine root 3x. Now, remember that root 3 closes off before the x. So, all right. Now they have use of computers, they say here. I'll let you read that if you find it helpful. But it shows you some things that you might run into in real life. 4.317 d4y dx fourth plus 2.179. There ain't no way you're going to factor that. But, you're going to have to use computers for things like that. So, enough said. Homework exercises here. Any of the odds 1 through 13. Any of the odds 15 to 27. Any of the odds 29 to 35. Either 37 or 39 or both. Do 41. And any of the odds 43 to 47. Any of the odds 49 to 57. And that you can stop. Yeah. Go with that. Now, let's move on to 4.4. Undetermined coefficients, which is part of that final exam, so maybe we can get enough done that you can do that one. I think when I've done this before, I think the people tend to respond better to 4.4, which is superposition approach, than they do to 4.5, which is called the annihilator approach. I had one class with one kid in it that said, "Oh, I want to do annihilator, that sounds cool." So we did that one. And then the others I've done in this one. And usually the undetermined coefficients, I think, usually win out. So let's do this one. I think they put it first because of that. Okay. Here is this is when you have, notice at the very beginning there, now you have no longer a homogeneous equation, you have a g of x on the right hand side. Okay? So what you start with is pretend that's a 0 and get your complementary function, y sub c, for the homogeneous part, which was what we were calling the general solution, but now it's called the complementary solution. And then you find any particular solution, yp, that will work for the g of x. Okay? So, the first two ways we'll consider for obtaining a particular solution for a non-homogeneous equation is the method of undetermined coefficients. The underlying idea behind this method is a conjecture about the form of y sub p, an educated guess, really, that is motivated by the kinds of functions that make up the input function g of x. So we look at the g of x and we make some guesses. I think I said this to you before. My calculus professor, when he had time at the end of Cal 5, we were in Porter System, and said, "Let me get you ready for differential equations." And he said, basically differential equations is you try tricks. If the trick works, call it a method. So that's what we're doing. We're trying some tricks here. Educated guesses. Okay? Now, if what we're limiting this to is differential equations, such as that first one that's listed there, where the coefficients are constants. Yeah, that's a given. The g of x is, and here's the given, either a constant k, not 0, a polynomial function, fine, an exponential function, fine, a sine or a cosine function, sine beta x or cosine beta x, or finite sums and products of any of those functions. That's sums and products of those functions. So strictly speaking, g of x is a constant that is a polynomial function, so that's sort of being redundant there. So here are some of the g of x's that we can deal with. If it's any other g of x than these, you're probably not going to be able to deal with it. So something like g of x is equal to 10, or 10/3, or 10 pi, or minus pi over 10, or any constant, okay? Or g of x is any polynomial, maybe x squared minus 5x, or minus 5, or minus 5x plus 3. Yeah, any polynomial, as long as you want to do it, okay? Now, I'm going to put this one in, g of x equal 8e to the minus x. 8e to the minus x. That's an exponential function. But you can combine a polynomial with an exponential, so you could have a g of x is equal to 15x minus 6 plus 8e to the minus x. I can't write. I don't know why I'm going so wacko with my pen here. Okay, let me see if I can clean that up a little bit. Oh man, I'm getting so hungry. Okay, sorry. We're getting close to 11. Oh. Okay, so any, and notice, here's another thing. It said product or sum or difference. So here, notice we had e to the x, then we multiplied it by a constant. That's fine. Here we had a polynomial, added it to an exponential. That's fine. Any kind of combination you have of these. Here's another one. I'm going to start with this one. The g of x could be sines and cosine. So sine of 3x minus cosine of 2x. That would work, okay? But not just that, you could multiply any part of that by a polynomial, say. So that could be a sine of 3x minus a 5x cosine of 2x. That's okay too, okay? It could get a little complicated, but you could do it. Here's one. A g of x is a product of some of these things. Product of a polynomial x, e to the x, an exponential, sine x. That works too. Or add to that a product of a polynomial, 3x squared minus 1 times the e to the minus 4x. So you could just about do not anything. Notice you can't have a log x in there. You can't have a tangent x in there. You can't have a 1 over x in there. Okay? You can't have negative exponents of your powers. You can't have, I don't think you can have, well, anything you can rewrite this way. For instance, I was going to say you can't have an exponential function with a base other than e, but yes, you can, because you can convert that to an exponential with a base e. So they do get pretty complicated when you start doing that, but you can do it. Okay? That is, g of x is any linear combination of any of the functions of these types. Okay, here's the most general. Okay? Polynomial functions, that would be a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus dot 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 all the way down to a1, let's say a2x squared plus a1x plus a0. Any polynomial function. You like them a little shorter than that, but they are. And then any polynomial function, p of x, or any of those kind, times e to the alpha x. That works. Okay? Any polynomial function, p of x, times e to the alpha x sine beta x. Okay, that works. Okay? Any polynomial function p to the x, p of x, multiplied by an e to the alpha x cosine beta x. Any of those forms will be perfectly fine. Okay? And like I said, not applicable for logs, not applicable for x's in denominators, not applicable for tangent x, inverse sines of x, secant x, cosecant x, hyperbolics, none of those. Unless they can be written as one of the other ones. I started to say hyperbolics, they could be written as e's. They always can be. Okay, so let's do example 1. That's what we can and can't do. So let's do example 1. Y double prime plus 4y prime minus 2y is equal to 2x squared minus 3x plus 6. All right. Now, first thing we do, step 1. They actually combine some things, but let's do. First we do the homogeneous form. Y double prime plus 4y prime minus 2y equals 0. That will give us what we'll call our characteristic solution. So what do we do first with that? E to the mx, that's going to be where we start, and you come up with the auxiliary equation, which is m squared okay, and a big boo hiss here, that will not factor either. Okay, so let's try our, make sure I wrote it right. Yes, I did. Okay, and that would be minus 4 plus or minus the square root of, say again, 4 squared, which is 16, minus, oh no, I like to count my minus signs. Minus 4 has a minus sign, A doesn't, this does, you have 2 minus signs, that makes this a plus. Very good. And let's just multiply those numbers together. 4 times 2 is 8. Okay? Divided by 2, okay, which becomes minus 4 plus or minus the square root of 24 over 2. This is minus 4 plus or minus, any perfect squares hiding in 24? 4 times this, so that would be 2 root 6, right? Over 2. 2 goes out, and that leaves a 2 there and 1 there. So our m is minus 2 plus or minus root 6. Okay? Now, this isn't this is irrational, but it's all perfectly fine. So basically, let's write this as m1 is equal to minus 2 plus root 6, and m2 is minus 2 minus root 6. Okay? So what will that give us as our solution? This is our YC characteristic solution will be C1 e to the minus 2 plus root 6 x plus C2 e to the minus 2 minus root 6 x. Those are the two. All right. And I really don't see much of a need to try to simplify those. They're just there. So that was the easy part, getting the characteristic solution. Now, how do we go about guessing on the particular solution? They haven't really given us a lot of guideline here, but we do know the particular solution, or at least a big first guess of it, will be this, that yp is going to be some form of, since that's a polynomial, let's just guess it's going to be ax squared plus bx plus c. Now, not to be confused with the a, b, c's that we just dealt with. This is here. We see, that's our guess. That's what we're guessing. And then what we have to do is take the derivatives. So yp prime would be second 2ax plus b, and y particular double prime would be 2a, wouldn't it? Okay. Now, let's plug that into what we've got here. That would be a 2a plus 4 times your y prime. So that's going to be 8ax plus 4b. See where I got that? 4 times the y prime. 8ax plus 4b. Right? Next, minus 2 times your y. So that would be a minus 2ax squared minus 2bx minus 2c. All right, so that's our derivatives added together, and we hope this is going to equal to 2x squared minus 3x plus 6, right? Now, looking at the big picture there, I only see one term with an x squared in it. This is a, right here, minus 2ax squared. That's got to equal 2, right? Minus 2a has to equal 2. Well, that's going to have capital A is equal to minus 1, right? So if you match those up, you get minus 2a is equal to 2. So a is equal to minus 1. All right, we got that. Okay, now let's simplify a little bit. So that gives you a minus 2, if a is minus 1, plus, no, minus 8 yeah, okay. Okay. Minus 8x plus 4b, we'll forget about the x squares. No, we'll write it down. Plus, I'm not worried about that. Let's write it down. Plus 2x squared minus 2bx minus 2c. Supposedly that's equal to 2x squared. So those go out. We can forget about that. Minus 3x plus 6. Right? So let's look at our x terms. Here we have a minus 8 minus 2b. Those are these two x terms. And this has to equal minus 3. Well, let's add 8 to both sides. And that gives us minus 2b is equal to 5. Ew. So b is equal to minus 5 halves. All right. So let's see what we've got now. We've got a minus 2. We've taken care of the x's, I think, fairly well. Plus, I don't know. I think it's a minus 10. If our b is minus 5 halves, multiply it by 4, that gives you a minus 10, right? Minus 10 minus 2c has the equal to, I threw out the x's, 6. Okay? So this is a minus 12 minus 2c is equal to 6. Add 12 to both sides, and that gives you minus 2c is equal to 24. Oh, I add the 12 to both sides and add it. That's 18. Sorry about that. So c is equal to minus 9. Okay. I think our particular solution now is the a was minus 1, so it's minus x squared. Our b was minus 5 halves, minus 5 halves x, and our c was minus 9. Okay, there's our particular solution. Now, don't have enough room, so I'm going to erase this stuff in the corner here. I hope I'm not erasing anything I need. Okay, so our general solution, y, is going to be the combination of our particular solution, c1 e to the minus 2 plus root 6 x plus c2 e to the minus 2 minus root 6 x plus, well, minus x squared minus 5 halves x minus 9. Let's see if that's what they got. Y, our general solution y is c1 e to the minus, they put that first, minus out front 2 plus root 6 x plus c2 e to the minus 2 plus root 6 x minus x squared minus 5 halves x minus 9. Yes, there's our solution. Make sense? Okay. Almost 11. Want to try another one, or you want to call it quits? Okay. All right. So let me, sorry we didn't, if we hadn't lost, basically we lost a week and a half out of 10 weeks. So we had a 8.5 week, 10-week term. So that's not very good. 3 more classes, we could have gotten a lot more covered. But do you feel confident you have a good starting point anyway? Okay. So let me give you this test.
Okay, and I'm going to give you my paper and my test too.
Okay. Now this says test 2, but it's not. Okay, so don't worry about this. Now I'm trying to remember if we did. Yeah, I'll take them if you want to. Okay. Keep you from standing there. Okay. Let me just go back and see if in the early thing, didn't we do? Yeah, we did linear independence and dependence. So I think you can, oh, here, yeah. Here's your test. Okay. I got it for you and then I started looking at it. Duh. Okay. Let me get one so I can look at it. Okay. So you can do number 1. I hope, Marcus, you're listening. And number 2, you can do the left-hand questions. We didn't do variation of parameter, but we did enough with undetermined coefficients that you should be able to answer those. And, okay, in number 1, those A through H, what you put in the blank is dependent or independent, independent or dependent, whatever. Okay, number 2, A, B, C, A through F, you can put yes or no in those blanks. Forget about in the first blanks. The second blanks you can leave blank because we haven't done variation of parameters, right? Okay, so do the first blank, but we haven't done the second. And then problems 3 through 6, oh, that's a 3 through 5. There is no 6. 3 through 5, I think you can do all 3 of those. 3 and 4 are homogeneous, and number 5 requires a particular solution, and we just did one like that, except we didn't have an e to the x in it, but I think you can guess what your answer is and try to do it. Say again?
I was just saying I think I could do it.
Okay, so basically you can do the whole test except the variation of parameters. You can leave those blanks. Okay, good deal. So you got a decent test. A fairly short test, and I think relatively easy test. I hope so anyway.
I think it is.
All right, good deal. Enjoyed having you in class, and please do your course evaluations, and you can get those back to me anytime. If you finish it today, you can bring it by today. I'll be here till 5:15. If you don't finish it today, let me give you my hours.
Yeah, I'll be here Monday. Like, my class is at 4.
Right.
And we get out at like 5:30 or 6.
Okay. I'm here for Monday and Wednesday from 7:45 in the morning until 9:15 in the evening. So I'll be here Monday or Wednesday. Tuesday and Thursday of next week, I'll be here 7:45 in the morning until 5:15. Okay? Now, understand Monday I'll be in class most of the day, so and I'll be up here most of the day, so if you don't want to bring it to me in class here, you can take it to my office and you know where that is. Tuesday, I'll be in my office almost all day. I do have an exam at 12, and we'll probably be through that by 2 o'clock. I'm guessing we'll be through by 2. So except for 12 to 2 when I'll be up here in the classroom, the rest of the day from 7:45 until 5:15 I'll be down in my office. And Thursday, all day down in my office, 7:45 until 5:15. And please get it in before noon on Thursday if you can. Okay? Good deal. So